Today, our team will present our project, Grid Harmonic Detection System. This project is about checking the power signal and finding harmonic in the electrical grid. So, next page, please. So the power grid in Mexico works at 60 Hertz. However, some devices like computer, LED lights, and motor drivers can make the signal less clean. So our project tries to detect this problem and show the condition of the grid in real life. Next, please. So for our project objectives, the main goal of our project is to build a system that can read, analyze, and show the voltage condition. First, we use the ZMPT101B sensor to measure the 120-volt AC signal safely. Second, we use the Arduino to collect the data. Third, we use FFT to analyze the signal and find the different frequencies. Finally, the system should alarm when the signal is normal or when there is some problem. Next, please. So for the system architecture, this slide shows how the system works. The system has four main parts. The sensor reads the voltage signal and make it safe for the circuits. The Arduino collects the data from the sensor. Then the computer uses processing to analyze the signal. Finally, the result is shown on screen and also with LEDs.
Okay, moving to the slide 5, let's delve the implementation of the fast Fourier transform to ensure accurate diagnosis or processing PPLin follows three major mathematical steps. The DC removal. For this, we know that the Arduino works to 0 to 5 volts, and this produces a 2.5 volts DC offset. We have to remove this to avoid errors. Then we have the Hamming window, that is an error due to the recollection of data, causing abrupt cutoffs of the edges, creating artificial high frequency noise. This is called spectral leakings. For this, the Hamming window forces the bounces of our data blocks to 0. This produces a good reading, a good distribution, and sharpness. Finally, the magnitude normalizations. For this, we know that the fast Fourier transform give us magnitudes of the frequency that it repeats. But for the detections, we need the voltages. That's why we normalize it and we get the voltages. And finally, the performance. The optimized PPLin allows the system to track out 7 harmonic, which is 420 Hertz, which maintain the incredibly precision frequency resolution of 1.95 Hertz. Following with this, we have that the colors that we use, the green establish a safe operation range with not harmonics or range upper than the range. Here we have the yellow that is approximate to the limit, that is higher to 0.1, and we have the red alarm. We have the safety range over a 0.3. Over in the RMAX, then we have the white LED that is turning on when the Arduino and the laptop is more than 3 seconds without being connected, and the green identifies the specific high harmonics causing the violations in real time. Then we have the mechanical design. For this, we follow the strict dimensions. For this, we use a generic PLC. And for material optimizations, we identify that making more while loops than infill will produce a more resistant to the 100 kilograms. And for that, we reduce also the grams using the pieces.
The code was separated into two parts, one for the sensor and another for the recollection and graphing, the combination of which leads us to proper readable results. First, the Arduino sensor, as we can see in the flowchart, we can see that it is reading at 1,000 Hertz at a 1 millisecond intervals, managed by a microcontroller timing structures and set up delays so that it can continuously monitor a voltage sensor connected to the analog input. The raw digital values obtained from this analog to digital converter are then streamed to the connected computer over a serial interface. But also beyond data collection, the Arduino also functions as a responsive indicator display. It listens for incoming single character status updates and sent backwards from the computer. And once it receives a command, it changes the internal state to match for the LEDs that we have. Those being for no network white, normal status green, alarm 1 yellow, and alarm 2 red. And it also has a built-in 3-second timeout protection for if the computer communication is lost, whether it enters the non-network state.
Finally, the other part of the code is the fast Fourier transform and the harmonic evaluation, where using the library minim is performed the transformation, and using the parameters set as Rmax and alarm 1 max, we can compare the values of the harmonics and the noise on it to see how what alarm will be shown in the display and in the LEDs. Here is the flowchart of those parts. You can see how we can analyze the system analyzation just to put all the human interface and all the graphs that will be set. We have the main loop where it's compared, we call to the different functions to call for the fast Fourier and the harmonics, and the signal processing where it's calculated 512 raw samples that are clean, normalized for the analysis, and then are transformed into the harmonics magnitudes, and are compared with the limits to set the alarms in case of needed. Here we can see a video of the box working on real time. We can see how this was during high demanding electrical parts, we can see that the alarm one is turned on. Finally, these are our conclusions.
So we achieved successful system integration by isolating the Hall voltage sensing layer at a 100 Hz precision, so we can obtain real-time frequency domain processing and also a visual dashboard. The algorithm and control validation using fast Fourier transform pipeline identified the anomalies that we needed to identify, while we were also able to minimize communication overhead by transmitting the state changes to the hardware LEDs instead of also being code and generating some noise. When it comes to mechanical and electrical durability, the physical print was successful in our test of supporting a standard load of 100 kilograms in compressive force, similar to what our simulation showed. Lastly, for the areas of improvement of our project, we would like to upgrade the interface to allow live interaction modifications to the resistance max threshold from the slider, and also narrow the alarm filtering matrix to prioritize triplet multiples, which would strictly then comply with localized grid criteria.
That will be all the presentation. We will put a video of the system working on real time. Thank you so much.